In this video, we're going to be looking at a pendulum. So I drew a simple pendulum here. Up here at the top, we can treat this as the ceiling. We have a string coming down from the ceiling and a mass attached to the bottom of that string. These three stars I've highlighted are points of interest that I'm going to be talking about as we work through this example. To start, I want to look just at the pendulum, assuming that there is no friction and there is no air resistance, so there's no outside forces. So as this pendulum is in motion and it's moving, okay, it's going to start up here at the top. Let's wait till it gets there. A little bit more. Okay, so at this point right now, where the pendulum is at, we would say that if somebody is holding it there, it's not moving, therefore it has no kinetic energy. And at that point, it's at its maximum height that it can travel because the mass of the pendulum is up at the ceiling. Therefore, it has its maximum kinetic energy. If you were to release this pendulum, I'm going to release the pendulum. As it travels down, its velocity is going to increase and then it's going to decrease as it comes back up to the top at this point. And if there were no friction and there were no air resistance, this pendulum would just continue to go back and forth forever, reaching each point, and it would just continue like this. Oops, sped up a little bit there. It wasn't supposed to. All right. However, what we know is that there is friction and there is air resistance. So each time this pendulum swings, if I start it back up at the top, all right, each time I release it, it's going to go and it's going to pick up speed, but it's going to slow down after it reaches the bottom star. And it's going to go up the other side a little bit less every single time if it's allowed to go on its own. So it would release, it's got its maximum velocity, now it's slowing down, and maybe it reaches this point. If I let it go, or once again, letting it go on its own, now it would start to come back down, maximum velocity, maybe it reaches here. Let it go, maximum velocity, maybe it only reaches there. Let it go again, and it's just going to continue to slow down and go less and less until eventually it settles back down at this point here. To recap, as the pendulum was moving, when there was no friction, there was no air resistance, at this point we started it here, it had its maximum gravitational potential energy. The mass moved down, increasing in velocity till it reached this point. It had its maximum velocity, therefore it had its maximum kinetic energy. And as the pendulum continued to move up the other side, its velocity was decreasing, but as that velocity decreased, we had kinetic energy being turned back into gravitational potential energy. And if allowed to go on its own, with no friction, no air resistance, it would continue moving back and forth like this forever. However, when we look at friction, we look at air resistance, and we factor those in, we know that if we release it up here, it's going to travel, it's going to go down, it's going to reach its maximum kinetic energy, but now all that energy cannot be converted. It's going to stop somewhere about here because it's losing energy to thermal energy. Whenever there's friction, friction's generating heat, and so we have energy loss due to thermal energy, and we're going to see it stop somewhere around here. Its gravitational potential energy is no longer what it was before. So as it comes down, once again, it's going to gain velocity, it's going to come back down, maximum velocity, but it's losing energy, it's not going to go as high. And so maybe it'll stop about here. And we're going to watch this progression keep going back and forth, going less high each time, until eventually we see it end up stopping. Remember also that the length of the string isn't changing, so although I drew those arrows moving down like this, okay, the pendulum's still going to stay in these paths. The arrows are just showing where its end point would be. So it would end here, here for that point, here for that point. To model this using an LOL, we're going to look at 3 points. This is going to be our starting point up here, where we're going to say that the velocity is equal to 0. We're going to look at this middle point down here where our velocity is at its maximum, and we're going to look at this ending point up here. We're going to assume this is how high up the pendulum would swing given if there was friction and air resistance, and the velocity is going to be 0 again. So to recap, pendulum's up here, it's swinging down, Vmax, it's swinging up and coming to a brief stop. If we were to look at after that, it would start to come back down. But these are the 3 points we're going to be looking at here. When we go to complete our LOL here, the first thing that we're going to do is write in our description of what is happening. So our description would be something like, for the first part, the mass of the pendulum is held up, then released, allowing it to fall freely. Correct that. And so there's our description of what's happening. Now we want to track it. And we said at its maximum height, its velocity was 0, so we have no kinetic energy. But it has height, therefore it has gravitational potential energy. So in potential energy here, switch to the pen tool, potential energy, we would say gravitational. That was a bad G. Gravitational. And we draw in some blocks here, and then remember that I like to write inside what we're dealing of, but it's going to be too difficult, so I'm just going to put a P for the pendulum. When we look at the middle position, that was when our velocity was at its maximum. However, we don't see all of the energy converted because we have friction, and friction is an outside force that's causing us to lose some energy. So when we draw our boxes, I don't know, we'll just draw maybe 3. All right, and this is still of the pendulum, and friction, we say, generates heat. Heat is a form of thermal energy that gets lost to the surroundings. So we have some thermal energy there, and I'm going to put a little F in there because of friction. So in our energy flow chart, what we would want to write is that gravitational potential energy is converted to kinetic energy, and some energy is lost due to friction. Moving from the bottom up, as the pendulum continues to swing in its motion up, we're starting now with kinetic energy. So we have kinetic energy. The thermal energy that we had here, we're saying, is lost to the surroundings. So we've got kinetic energy that's going to get lost, and it's going to be converted to kinetic energy as that pendulum is swinging up. Now, there's still friction, there's still air resistance, which means we're going to lose even more energy to thermal, so we're not going to see all of that kinetic energy going into gravitational potential energy. So, we would draw this, and we would draw even less boxes here, and label that P for the pendulum. And once again, we have, and this is gravitational, we have energy lost to thermal. So I'll come over here, and I'll label that box F. I forgot to put in our description here, so I just added it real quick. I said that the mass of the pendulum continues its upward swing, decreasing in velocity until it stops at the top. So to recap here, we looked from the beginning. We had the mass of the pendulum. It was held up. It had gravitational potential energy. It was released. That potential energy was converted to kinetic energy. Because of friction and air resistance, we lost some energy to thermal energy in the form of friction. All right, but the majority of our energy was converted to kinetic energy. That pendulum continued its upward swing. Its velocity was decreasing, and we had kinetic energy being converted back to gravitational potential energy, but we still had some energy that was lost to thermal energy. So once again, we're keeping track of where that thermal energy is going. We don't rewrite this anywhere, all right, because when we have the thermal energy, we're going to say that it gets lost to the surroundings or to the environment.